right. So, last time I showed you this, right? I showed you this, right? And what did this do? Well, at the end, yes, but before it broke, what was it doing? It was just counting up by 1. So you look at this code and you say, well, there's clearly no loop in it. There's no loop. I don't see a while loop. I don't see a for loop. Yet this code was run repeatedly with a slight change every time with the value of n. But this is just another way of looping. When you think of what a loop is run this code multiple times. A function call means run this code. So if you have a function call making a function call to itself, it's just going to keep running itself over and over and over again. It's the same idea. So I run this, but eventually it breaks. And the reason it broke was because based on just how these computers work and how Python is designed and the programming languages and whatnot, there is a limit on how many functions can call other functions and so on and so on and so on. There is a limit. But that limit isn't something that is intrinsically true for recursion. It's just a consequence of how these computers work. So it's not recursion that has some hard limit. No, it's just the computers that do. So be aware of that. So something recursively defined is not always going to break or something. It's just, again, the computers. Yeah?
Theoretically, if
With what I assume you mean, kind of, yeah. It'll just take up more and more RAM. So it won't be on a stored on long-term storage. It would just be stored in RAM, and then eventually your computer would just vomit, But yeah. And there are settings you can change to increase the maximum limit, but yeah. Any other questions about this? Now, typically, yeah.
I have a question. Are we going to have a review class next week or no?
No, I don't think so. No. Any questions about this? Typically, if you want to use recursion for looping, you have some base case, some case that kind of stops the recursion. If you think back to that linear search that we did with recursion, it actually had two base cases that stopped the looping, that stopped the function calling itself. Does anyone remember what those cases were? I'll get comfortable. I'm fine. I'll take any guess. I can't actually hear you.
Oh, I actually missed the first half of the question, so I just didn't
Oh, I'll repeat the question, yeah. When we did the linear search with recursion where it was like calling itself, I showed it to you in Haskell and then I did it in Python. And the thing that makes it loop is whenever the function calls itself. But we need like a stopping point. Otherwise it just breaks like we see right here. There needs to be a point where it stops calling itself, and we call these the base cases. And the linear search had 2 of them. Any ideas what those were? Well, we did use if statements. We use an if statement for one of them, but what was the base case? There's 2. When did it stop calling itself? Well, think of the linear search one, right? When we were doing that thing with the head and the tail of the list.
One was when you had an empty list.
Yeah, that's one of the base cases. If we ever see an empty list, we stop. What was the other one? Say that again? No, I didn't. I said return false. What was the other base case? What else stopped it from looking? What did you do? What is that? I don't even. A wooden block makes sense. No. Let's rewrite that function. Exactly. If we ever see an empty list, there's no need to keep looking. And if we ever find it, there's no need to keep looking. So let's rewrite that function regardless. Return false. Oops, not that. Here was me writing it more like the Haskell one. And let's just do a quick check. True, 4, false, 9, true, and just check whether it's empty. False, yeah. So here is the linear search. In the 2 base cases, the way it's written here, it's kind of one of them's hidden. Hidden's not the right word, but one of them's not as obvious. So this is a base case. We used an if. If we ever see an empty list, stop looking. It's done. No need to keep going. And this is the other base case. But I can rewrite this. There. So now the 2 base cases are a little more obvious. This was like the first way we wrote it. If the haystack is empty, stop. You return something. If the thing at the beginning is what I'm looking for, stop. We found it. Otherwise, return the result of doing a linear search on the rest of the list. The tail. Everything after the beginning. So that's the trick with recursion, is you almost always need a base case. There are exceptions to the rules, like with most things, but typically you're going to want your base cases. Often you only have one, but whatever. So here's what we're going to do. You know, the trick with recursion is kind of thinking like lazily. You know, the way you can think about this is, if you asked me, let's say you're calling this function linear search, and I'm an instance of this function linear search. And you say, all right, check if needle's in this haystack. So I ask myself, okay, is haystack empty? No? Oh, all right. Is the thing at the beginning of the list the thing I'm looking for? Yes or no? No? Okay. Well then, I just need to know, in order for me to answer you, if you ask me if needle's in haystack, I checked if it's empty. I checked if the thing at the beginning was what I'm looking for. And then after that, I don't want to look anymore. I'm lazy. I'm going to offload that work. I'm just going to ask someone else to do the rest of the work for me. But I'm going to tell them to start looking, not at the beginning of the list, but at, you know, everything after the beginning of that list. And then that person is going to do the same thing, but with the shorter version of the list. You know, every time this is running, it's running the same code on the same data that's just a little bit like smaller every time. That list is getting smaller every time. And as it does, it works towards this base case of getting an empty list. But let's say, for example, let's change gears a little bit. And here's what I want to know. I want to know how many people are sitting here. All right? But I'm really lazy. I'm not going to count you. I don't want to count you. No, before I proceed, all of you are going to have to answer a question for me. It's going to be really simple. And what we're going to do is we're going to go from the bottom up, my left to right. So when I say the next person, just think, okay, is there anyone to your right? Okay, go behind and then left to right, okay? So that's what we're going to do. So I want to know how many people are in this room. So what I'm going to do, not in this room, in this chunk of stair, you know what, let's do the whole room. Just because there's only 3 more people, let's just have some fun. So we're still going to do bottom up, so you'll be the first person I ask. And then the next person that gets asked is you. And then you, and then you. That's how we're going to go, okay? Understand? I want to know how many people are in this room. So I'm going to ask you, how many people are in this room? Right? So now it's your job to tell me. You have to tell me how many people are in this room. But you're like me, you're lazy. You don't want to count. So what you're going to do is you're going to go like, well, I know that the total number of people in this room is going to be you, 1, plus however many other people there are in the room. So all you need to know to answer my question is how many other people are in the room, add 1 to it, you, and then tell me. Right? But then, of course, that's a bit of a problem, is, well, how do you don't just know how many other people are in the room. But I got good news for you. It's not your problem to find that out. It's her problem to find that out. So you need to ask her, how many people are in this room?
How many people are in this room?
Like after you, yeah. So you go, oh shit, I don't know. But you do know it's 1, you, plus however many other people are in the room. So you just need to know how many other people are in the room. So ask him. And what do you say? Oh, well, it's 1 plus however many other people are in the room. So ask him. Speak up. No one else can hear you. And what do you say? Well, it's 1, you, plus. So ask him. But what do you know? Exactly. So you just need to know how many other people, but like behind you, of course. So ask him. Exactly. Everybody else plus you. So you just need to know how many other people are there. So you got to ask him.
How many people are in the room? Myself plus however.
So you better ask him.
How many people are myself plus how many other people are in the room?
So you better ask him.
How many other people are in the room?
Myself plus everyone else.
You, so 1 plus everybody else. So you better ask him.
How many people are in the room? Myself plus everybody else.
And everybody else, well, that's, I guess, him, so you better ask him. Yeah, you guess. So you better ask everybody else, which is just her back there. 1. So you say, well, it's you plus everybody else, but how many other people are there? No one. So if you know there's no one else behind you, the question is, you know the answer is 1 plus how many other people are in the room. You know how many other people are in the room behind you. It's 0. So you know it's 0 plus 1. So how many people are in the room, including you and behind you? 1. So you better let him know that. It was 1. So you know how many people are in the room, including you now. There's 2. So you better let him know. So how many including you? Well, you better let him know. He asked you. You better let him know that. Don't tell me, tell him. So 4 plus how many plus you is how many? 5. Well, don't tell me, tell him.
How many people are in the room?
No. You tell him 5.
5.
Hey. Uh-oh. Our algorithm broke. 8. So 11 plus you is 12. Oh, so you tell me it's 12. Oh, so there's 12 people in the room. Yeah, there are. Well, look at that. But did any one of you count everybody? No. You only counted yourself and then asked the next person how many other people are in the room. You answered that question recursively. But notice that, like, in order to answer that question, I asked you, and then we had to go all the way down, and then all the way back before I got an answer. But no one person counted everybody in the room, but everybody counted themselves and just relayed that information. So it wasn't like one person counted 12 people. 12 people just counted themselves, plus everyone else behind them, right? Which is kind of neat. So that's what recursion is. And a lot of times, so if you couldn't see, the function calling itself was the how many people are in the room behind you and behind you. That was the recursive call. Every time you asked somebody else, that was the recursion. Then we hit a base case, which was you. We got to the problem, or not the problem, got to the situation of, well, there's an end. There is a stop to this, where you can finally start to answer the question. Here, if you've got your computer, I'm going to give you 3 minutes, and I want you to write a function, sum to n, that returns the sum of all integers between 0, so you have to include 0, return the sum of all integers between 0 and n. You can include n. If you end up writing it such that you don't include n, not a big deal, but you can include n. And you do it with a loop. Do it with the way that you know how. we can just start. Raise your hand if you're done. So did anyone do it basically like this? Did anyone do it with a while loop instead? Yeah, while loop. While loop I think maybe is a little more natural in this case because it's kind of weird to do n plus 1 because I wanted to include n, but whatever. Yeah, and so this will obviously work. But I don't want to do it with a loop, with a for loop or a while loop. I don't. I want to do it with recursion. And the trick with recursion is, one, you got to think lazy. That really is a big part of it. You got to think really lazy. And you have to be able to notice when you can solve a problem, you have to be able to notice that a problem is actually solvable by breaking it down into the exact same problem. Which sounds weird, but like, look. I want to know the sum to 5. It's 15. But what's the sum to 4? Well, what the sum to 4 is 0 plus 1 is 1, plus 2 is 3, plus 3 is 6, plus 4 is 10. Right? So the sum to 4 is 10. So the sum to 5 is actually just the sum to 4 plus 5. Right? If I happen to know, if I asked you, what is the sum up to 5? And you said, oh shit, I don't know. Oh, wait a minute. I know the sum up to 4 is 10. I just know that. And if I know that the sum to 4 is 10, then I can easily calculate the sum to 5. It's just the sum to 4, which is 10, plus 5. But that, of course, requires that you just happen to know what the sum to 4 is, which you don't. But I got good news for you. There's a function that exists that'll tell you the sum to 4. And it's actually that function that we're currently writing. The sum to n is just n plus the sum to n minus 1. Right? If I want to just plug in 5 for a second. If I want to know the sum to 5, if I call sum to 5, what's n right now? It's just 5. N is 5. And then what's n minus 1? 4. So I want to know 5 plus the sum to 4. So I would just call the function what's sum to 4? Let's draw this out for a second. I'm going to represent sum to as like an f, just because I'm lazy. So if I want to know f of 5, you can all see this reasonably well? Yeah? Based on my definition here, I'm just saying it's 5 plus the f of 4. So that equals 5 plus f of 4. Bear with me. That's a 4. Right? That's what I'm saying it is. Sum of, remember, sum of is just f. So we could change this to an f if it makes you happy. There. Right? F of 5 is just is 5 plus f of 4. Right? That's what this says. But of course, we don't know what f of 4 is. So we have to figure that out. And f of 4 well, now the parameter's value is just 4. So what is f of 4? Well, that's easy. That's just 4. Based on this definition, f of 4 is 4 plus f of 3. Right? But of course, what's f of 3? Well, f of 3 is just 3 plus f of 2. That's a 3. Right? So far, so good. But what's f of 2? We don't know the answer. But because I can't answer what f of 3 is until I know what f of 2 is. Once I know what f of 2 is, it's just f of 2 plus 3. So f of 2, we got to know what that is. F of 2 equals 2 plus f of 1. What's f of 1? Well, we don't know, but that's the definition says it's f of 1 equals 1 plus f of 0. And what's f of 0? Well, f of 0, according to our definition as it is, f of 0 should be 0 plus negative 1, which I squished in there. According to the definition, it's 0 plus negative 1. Because when n is 0, well, 0 plus f of 0 minus 1, which is negative 1. But I wanted to know the sum of 0 to n inclusively. So I actually don't, like the sum up to 0, saying it's 0 plus f of negative 1 isn't quite right here. I wanted to stop at 0. I really only cared about positive integers. So really what I could say is, well, if n is 0, what is the sum up to 0? If n is 0, what's the sum up to 0? That's our base case. If we ever see a 0, well, the answer is 0. So now we could actually go back here and be like, well, f of 0, no, that's just 0. Get rid of that. And because I know f of 0 is 0, I can actually replace this right here with a 0. Which means f of 1 is what? Tell me. 1 plus 0, which is, of course, 1. So this is actually just 1. So f of 2 is what? 2 plus 1, which is? So f of 3 I can now answer because I know what f of 2 is. So what's f of 3? 6. And because I know what f of 3 is, I can finally answer f of 4. What's f of 4? 10. And because I finally know what f of 4 is, I can finally answer what f of 5 is, which is, of course, 15. So the answer is f of 5 is 15. But what's neat here is we started asking the question up here. We had to go all the way down and then all the way back in order to answer the question finally, right? This is a common thing you see with recursion. Down and back. You start somewhere, you go all the way down to the bottom of the bucket, and then you work your way back up. And see how, look, we've got this base case. The base case is kind of like a matter-of-fact case. Like, look, if I ever see 0, it's 0. I don't have to ask any questions. I'm done. If I ever turn around and see that there's literally no one behind me, there's no one behind me. That's like the obvious case. But then the recursive case is, like, look, this problem is actually, I can answer what f of n is by answering the exact same question on a slightly different version of the same problem. I can answer what f of 5 is if I could answer what f of 4 is. And see how when I say like that slight variation of the same problem, that slight variation was actually like a step towards that base case. When I subtracted 1 from n, it got me closer to 0. Now, here's a quick little quiz for you. What's going to happen if I put this in? Look at this code for a second, and I want you to tell me what this is going to do. It's not a trick question, just what does the code say? Yeah. It broke. It gave up after a little bit. It ran for 3 seconds, and then it was like, yeah, I'm done. And why did it break? Well, just what does the code say? What's f of negative 1? Well, is negative 1 equal to 0? No. All right, so that means it's negative 1 plus f of negative 2. Is negative 2 equal to 0? No. With that input, we're actually never taking a step towards the base case. We're actually moving further away from the base case every time. If you start at negative 1 and you keep subtracting, you're never going to hit 0. It's not going to happen. Right? How many times do I have to subtract 1 from negative 1 to hit the number 0? Well, that's a stupid question because you can't. It's impossible. All right. Any questions about that? Recursive stuff? Yeah.
So this doesn't seem terribly efficient. Is there like less work to do the same thing? Is that the loop?
So there's 2 ways to answer that question. And I see your hand too. Just give me a moment. There's 2 ways to answer that question. It's not less efficient. It's not. In terms of what it means computationally, it's not. It's equivalent. There's really not much of an efficiency idea in this terms of just like atomic units of computation that are taking place. In fact, recursion is far more of a natural way of doing iterative processes. In nature, when you look at anything that is like a pattern, these patterns are based on applying the same properties on existing properties. Like when you look at ice crystals forming, ice crystals form based on some rules, and they form based on the crystals that exist before it. Like that's recursive. There's no for loop in nature. There's no while loop in nature. All of these things in nature that have like iterative processes are recursive. So recursion is actually a far more natural way of looping. To you, because you're used to for loops and while loops, you look at this and you think it's weird. There was a time where I spent a year only using functional programming languages, and when I went back to C# and I had to use a for loop, it took me a while to I was like, how do I loop again? Like I couldn't make that switch back because I was so used to recursion. It was difficult for me to go back to loops. So don't think, oh, recursion is just this more complex way of doing loops. No, it's just a different way of doing loops that you're not familiar with. Anything you do with recursion, you could do with loops and vice versa. That said, in terms of how these computers work, recursion is really shitty. Recursion is actually less efficient based on the overhead of how these computers work, which we will talk a little bit about next semester so you can get a sense of why that really is. But that's not because of recursion. That's because of how these things work, right? So, you know, you got to think, when I give an algorithm to someone, some computational system is executing that algorithm. When I write Python code, the computer's running that algorithm. But I could give that same algorithm, I could code up in Python the algorithm for a linear search. But I could also explain the algorithm of a linear search to you, a human, and you can do it. I can write the code to sort stuff. But I could also tell you, a human, the instructions to sort stuff. And you're the computational system doing it. So it's the system's features that made recursion slower. Now, there are some things about recursion that sometimes, you know, anything you do with loops, you can do with recursion. Anything you do with recursion, you can do with loops. And sometimes writing something recursively is just so much more simple than doing it with a loop. Like it's just elegant. It's simple, it's nice, it's clean, it's very descriptive, it's awesome. But being aware that, well, computers actually suck with recursion, that could be a problem. But there are several modern programming languages that do, you know, every time you write code and you hit run, the code you write has to get converted into like zeros and ones that your computer actually runs. Low voltages and high voltages pumping through the processors and all the transistors. That's how computation happens on these computers. But what's interesting is the code you write, if I were to translate the code you write directly to the corresponding zeros and ones, you wouldn't get what Python does. You wouldn't get what a lot of modern programming languages do. What a lot of modern programming languages do is they will do optimization on your code. So it'll look at your code and be like, okay, that's great, but we can actually do this more efficiently by doing it this way. And what's awesome about that feature is it really goes back to what I was saying at the beginning of the semester. Computer code is not for computers. It's for humans. It allows you to write the code in a way that can be self-descriptive, but perhaps less efficient. But you don't need to worry about that loss of efficiency because Python or Java or C++ will actually take care of it for you. Computer code is not for computers. Machine language is for computers. Zeros and ones are for computers. Code is for humans. In order for your computer to run your code, you need a program like Python to convert your code to what the computer cares about. Python code is for humans. Java code is for humans. So what's really interesting about Java is Java does tail-end recursion optimization. So depending on the style of recursion, Java will actually go out of its way and be like, look, I know you wrote this code recursively, but we're going to pretend you wrote it iteratively with a loop, because I know it's going to be faster and more efficient. So you could actually write recursive code, but it's going to run as if it was iterative, which is awesome. So that's a neat little feature there. And there was one other thing I was going to say about it too, but I can't quite remember now. But hopefully that was sufficiently answering your question. You had a question.
Yes, I'm not entirely sure how to phrase it, but I'll do my best.
So that's because what you were doing wasn't recursion. So the reason this stopped running wasn't because of the runtime. It was because of the number of call frames that were added to the system stack, which is just gibberish to you. I realize that. But that's why it broke. The runtimes, I can write code that'll run for 200 hours. I can write code that'll run forever until like the power gets turned off. So that is a separate issue. The runtimes that you had was just the stopping criteria wasn't met yet. And I'm guessing that happened because you had a really high spread probability and or low cure probability. No. A low spread probability, but a high cure probability. So the world never got completely infected. Yeah. Is everything okay? What's going on? What did I miss? You don't have to tell me. Any other questions? Now, have any of you sorted anything before? Put up your hands. Of course you have. My 3-year-old can sort things. You've sorted things. Whether I give you a collection of blocks with letters on them, or a stack of exams with names, or a giant pile of numbers I want you to sort, you can sort them. And you're going to follow a series of steps, assuming you are capable of sorting things, which I really hope you are. You will follow some number of steps that you start with an unsorted collection of things. You follow some steps, and then at the end, you end up with a sorted collection of things. So those steps that you're following is a sorting algorithm. You sorted things based on some series of steps that you took. But what were those steps that you took? You know, you kind of just intuitively know how to sort things. But how many times have you been sorting something and you thought, like, what are the atomic steps I'm actually taking that's resulting in finally getting a sorted collection? You probably didn't really think of that. Maybe you did, and if you did, you're weird, but I like it. But you did follow some steps. But what were they? So here's what we're going to do. It's the weekend now, right? And we're not going to have time to go into any of the sorting algorithms or talk about them right now. We can get to them on Monday. But think a little bit about what were the steps that you followed to sort things. Figure it out. And then on Monday, we're going to talk about some examples of what people have been doing. Because here at the end of the day, how many ways are there to sort things? There's a good answer to this. An infinite. I mean, a lot of them are going to be garbage. But just because, like, if I gave everyone in this room a collection of things to sort and told you to sort it, I'm willing to bet I'm going to get several variations. I'm going to get several different algorithms that all worked. We're going to talk about some sorting algorithms. And I want to be clear. You might say, okay, searching, yeah, that was easy. Sorting, okay, yeah, searching and sorting, yeah. But sorting's non-trivial. Sorting, we're going to look at some sorting algorithms, and no one's going to expect you to look at that algorithm and be like, I know what it does. It takes time to look at them and to understand what it's doing. These are non-trivial. I'm not saying they're complicated. I'm saying they're non-trivial. So it is tricky stuff. And you might say sorting, okay, how in human history, how many hundreds of thousands of years do you think humans have been capable of sorting things? Probably several hundreds of thousands of years, if not a hell of a lot more than several, right? But you want to know something wild? Is, first of all, the sorting algorithms you're gonna come on Monday and be like, hey, yeah, this is what I do. They actually suck. It's actually not that long ago where people discovered like, oh shit, there's a way better way to sort things. So you might think sorting, whatever. Yeah, but for how many hundreds of thousands, if not millions of years were people sorting things? It wasn't until like the last 75 that someone was like, wait a minute. If we do it this way, it's way better. And we already now know what it means to be better when it comes to an algorithm, but we'll pick up here Monday.